topic we're looking at right now, finding limits numerically and now graphically. This topic corresponds to section 2.2 in our textbook. And really we're going to be looking at how to evaluate the limit of a function based upon a table of values, or if you visually have a picture of the graph. So we really want to approach this as thinking of a foundation upon which to build our entire study of calculus. Think about if arithmetic is the foundation to algebra, limits are the foundation to calculus. To do calculus, we really need the limit concept. So algebra is very static. You're looking at what the function is, what something is evaluated at. The idea of a limit is a little different. So it's all about behavior, what the function is doing as you move along the x-axis, as your independent variables change. What is the behavior of a function or a graph? What is happening? So we're not really interested right now in what the function is, but what it is doing. Because you got to kind of separate those ideas. Algebra, what the function is. Calculus, what the function is doing, okay? So let's consider this rational cubic function. Okay, x to the third minus 1 over x minus 1. When x did not equal 0. Okay? So, of course we know, because of our algebraic studies, this function does not exist at x equals 1. So you're really looking at what is f of x approaching as x approaches 1. So you kind of have to keep track of two things mentally. As x changes, y is also changing. So as this one changes, what happens to this one? Horizontally, as we move, where are we going vertically? Now it's kind of the saddest story in mathematics. We're going to go somewhere. We're going to get closer and closer to x equals 1, but we'll never get there. It's kind of a sad story. We're going to get there, go there, we're going to travel there, we're going to move there, we're going to try so hard, we can try so long, but we'll never get there. If we're never going to get there, can we predict what would happen if we got there? So based upon behavior, what should happen, assuming nothing crazy comes up? So for this graph, as you're approaching x equals 1, you're coming in from the left. So you're kind of tracing along, you go down, you reach a minimum, you come back up. And you're also approaching from the right. And what happens? As you come in from the left, as you come in from the right, do those two behaviors converge towards each other, so you have convergent behavior, or do they diverge away from each other? So you don't have something, you don't have one value you're approaching. So visually, looking at the graph, as you come to the left, as you come to the right, are you coming towards yourself? Your right hand, your left hand. Are you coming towards, or are you going away? So visually, the graph, you can look at it, you make a prediction. And as you look at this, you're like, you know what? We're coming up towards 3 as you come from the left. So as you come to the left, we go down, we come back up, we're kind of going towards 3. As you come from the right, you're going down, and your y values are getting closer and closer to 3. But again, remember, this is the saddest story in mathematics. You'll never truly get there, because there doesn't exist. But if we got there, what would happen? Now, if you look at a table of values also, if you were to plug in 0.9 for x, you plug it into a calculator, you get 2.71. Plug in 0.99, 2.970. As you plug in 0.999, so you see the pattern, we're just adding a 9. We're getting closer and closer to 1. You get 2.997. So you see our x values, they're going up. 2.71, 2.970, 2.997, going up, but you're also going up at a slower rate. You're kind of coming up and you're slowing down, and they look like we're getting closer and closer to 3. As you come in from the right, so values greater than x equals 1, plug in 1.1, and I'm not a genius, I have the numbers written down here. In case you're sitting there like, wow, what a smart guy. To be honest, I have them written down. And you plug in 1.01, 3.030, and you plug in 1.001, 3.003. So again, it looks like as you come in from the left, as you come in from the right, looks like we're getting closer and closer to 3. But remember, this is the saddest story in mathematics. Because if you plug in 1 for x, it's undefined. You don't get anything. So you can try as hard as you want to get to x equals 1, but you can never get there. You can get really, really close. You can get infinitesimally close, but you can never truly get there. Algebra is all about what a function is at 1. Calculus, what a function is doing as you get closer to 1. So as we come in from the left, which let's get some notation in here, okay? So this is from the left. So the notation we're going to use, the limit, LAM for limit, of f of x. So the limit of f of x as x approaches 1. Now we're coming from the left, so from more negative values. So you have that superscript, the negative sign. And as we come in from the left, based upon the numbers we have, we're like, hey, 2.71, 2.970, 2.997. We're going up, we're slowing down, we're getting closer and closer to 3. Now, let's repeat all that for the right side, for numbers greater than 1. So kind of like we did on the graph, just tracing along the curve, looking at the table also, tracing coming in from the right. So this is from the right. So again, using that notation, the limit of f of x as x approaches 1 from the right. And as we come in from the right, our y values are going down. 3.31, 3.030, 3.003. So we're going down, but we're slowing down. Getting closer and closer to 3. And you think, hey, how about that? From the left, we're approaching 3. From the right, we're approaching 3. The same thing, we have convergent behavior. So, these two values, we can kind of combine them together. So now, big brain, okay, this is huge. The limit of f of x as x approaches 1. No superscript, no minus, no plus. So the two-handed limit, the limit of f of x as x approaches 1. So the two-handed limit from both sides, from the left and from the right, all at once. We have converging behavior. We are approaching 3. So we have our limit. Now remember that we have the limit, we have the behavior, we don't have the function value. What is the function at x equals 1? It's undefined. That still holds true. That's algebra. At 1, it's undefined. But if we could get there, could we predict what we would have? And that is the calculus. If we could get there, we'd have 3. So algebra, what the function is, calculus is what could happen, okay? So some language we have an informal definition. What is happening to y as x? So as something is happening, behavior, as x gets close to a certain number. So in order for a limit to exist, we have to be approaching the same y value. So the same y value, this y value has to be unique. So converging behavior, going towards the same value, going towards two values, well, which one is it? You need one answer. So approaching some value c, c we use to denote an x value. Alright? So you need converging behavior towards the unique y as x approaches c, some x value. Now some cases where limits don't work, okay? Kind of show you visually how that happens. I don't need that, okay. So like if you're coming in for the left, the function stops. You're coming in from the right, the function stops, boy, you were going up, you were going down, but there's kind of a gap. That gap is no good. So what is the unique y-value? You need one value. So this limit, let's call this f of x. It does not exist, okay? Another example, you're pretty used to, you've seen this. Rational functions. So rational functions have that wonderful thing called a vertical asymptote. You know that vertical line running up and down, the function kind of goes toward it, then it's kind of going, then the function says nope, but they don't really communicate with each other, the two branches. One goes up, one goes down. That's divergent behavior. So let's say, well, I don't use pen, so let's say this is x equals 0. This vertical line. So the limit of our parent rational function as x equals 0. You can say it does not exist for that also. Now let's say the two branches were communicating with each other. One from the left goes up. One from the right also goes up. So you again have that vertical asymptote at x equals 0. So the limit of, let's say this is 1 over x squared. So x squared, every x value gets squared, so the fraction also is positive. So as x equals 0. Now they're both going up, but infinity is not unique. It's like the younger sibling syndrome. I can think of a really big number, the younger sibling. Well, I can think of one bigger. And you go, well, I can think of one bigger than you. Then the sibling, well, I can think of one bigger than you. It's a constant one-upping game. So what number is the biggest? What unique number is the biggest? So your limit has to be unique. Now here's one of many gray areas we're going to discover, okay? College Board will accept does not exist. Or in this case, they'll also accept positive infinity. Kind of look at it this way. The limit does not exist. There's no unique value. Does not exist. And they say, well, can you tell us anything about it? And you say, well, it's going up, infinity. So the limit doesn't exist, but there is some information. At least they're both going the same way. They're both going up. So looking at some graph examples of this, kind of going through filling it all in. So example 1, we're approaching what? 1. So of course this kind of interesting part of the graph here. As we come in from the left, we're going up and up or approaching 1. As we come in from the right, we're staying pretty level. We're approaching 2. Now 1 and 2 aren't the same thing. So overall behavior, what unique value are you approaching? that unique value does not exist. Now go back algebraically. Is there a filled in hole? Is there a true function value? What is the function at 1? Well, there's a filled in circle right there. So f of 1, you could say that's 2. Alright, so go ahead, take a look at the rest of those examples, and then check your work with my completed notes online.